In any hypothesis testing situation, there are two things that we need to consider. First, we're interested in whether we retain our null hypothesis or reject our null hypothesis. And we're also interested in the reality of the situation. So beyond our particular decision about our sample, null hypotheses are either true or they're false. So to put this into context, one study can test the effectiveness of an intervention. And that intervention can come back and say there's an effect of the intervention or there isn't an effect of the intervention. But over the long haul, which goes beyond just a single sample, the intervention is either going to be effective or it isn't. And so these realities are reflected in this kind of decision matrix. In any hypothesis testing situation, there is a potential for two correct decisions. I can retain a null hypothesis that is true, so I can correctly conclude that there is no difference between my means, and I can make a correct decision when I reject the null hypothesis. I can say that I have found a true difference between the mean. But the alternatives are these two errors. And in statistics, we refer to type 1 errors in terms of alpha, the Greek letter alpha. This is going to be what we call our significance level, our alpha level. And then I have beta, or my type 2 error. Now these refer respectively to false positives and false negatives. In which case, I'm saying that I have found an effect when the effect was found in error, and I fail to find an effect. And what's important for us to realize now is that these are inversely related to each other. So as alpha increases, beta decreases, and vice versa. I have control over alpha. I can set alpha to be 95%, 90%, etc. But I really have no control over the type 2 error. Now, just to put this into text, type 1 and type 2 errors refer to false positives and false negatives, respectively. So a type 1 error refers to an incorrect rejection of the null hypothesis, and the probability of this error varies with the level of significance that we choose. So if I choose, for example, an alpha level of 0.05, then my type 1 error rate is 5%. A type 2 error rate is kind of the inverse of a type 1 error. It refers to a false positive, and this refers to the probability that I'm going to incorrectly retain the null hypothesis. And this error can be reduced by increasing sample size. We express the levels of statistical tests with the use of a p-value, which is related to alpha. P-values refer to the probability that we're going to obtain the sample data if the null hypothesis is true. So the alpha level refers to the probability that the null hypothesis is incorrectly rejected, or the type 1 error rate. Now, when we're choosing a level of significance, we have to consider this type 2 and type 1 error rate. If I set a type 1 error rate, I want to do so depending on how risky it is to say there's a difference when there isn't. And so the probability of making an error when alpha is set to 0.05 or a significance level is set to 0.05, then my type 1 error rate is 5%. So let's think about this for a minute. If I want to test the effectiveness of a medication in reducing risk of death, then I'm likely to set my type error rate very, very, very conservatively, because I don't want to invest people's hope into a pill that I say is going to work if it actually doesn't. So that's type 1 error rate in action. If I research and develop a drug and my testing comes back and says that it's effective at lowering risk of heart attack, for example, and then I put it out into market, and once it gets taken by millions of people, it comes back and says, well, once we look at it across everyone, it actually is not effective. That's a type 1 error rate. Okay? Whereas if I have a more kind of business orientation, let's say, for example, I want to test the effectiveness of a marketing mechanism to increase the likelihood that someone is going to buy the product by 5%. Okay? A type 1 error might not be so expensive to me, whereas I might, it might be very important if I miss a statistical effect in that case. Okay? So in that case, whether or not someone buys a product is not as risky. Therefore, the likelihood of a type 2 error in that case might be more acceptable. Whereas the type 1 error associated with research and development of a drug could be actually quite profound, and so we might want to minimize that. So the choice of whether to minimize type 1 error or type 2 error in some sense needs to be made by the researchers or the practitioners so that you can decide which of those is more acceptable risk. Moving into kind of visualizing what this looks like in the context of the bell curve, if my level of significance is 0.05. I can look to the z-tables in the appendix, and I can recognize that 5%, okay, remember if alpha is 0.05, then that corresponds to 5% critical region. I have to divide that 5% across the two tails, and looking at those tables in the back of the book, we can see that 2.5% of the distribution in the tail is associated with z-scores of plus and minus 1.96. But we can see that as alpha increases, okay, from 0.05 to 0.01, okay, as our alpha level becomes more stringent, okay, then the area of the curve associating with that, our critical regions, become more extreme. Okay? So as I divide up 1%, okay, I'm putting only 5% in the tails, and that corresponds with a more extreme value for our critical regions. So putting this up a little more, okay, this is just an exploded version of what we just did. Okay? Again, if I have an alpha level of 0.05, I have critical values of plus or minus 1.96. And that value is literally the result of taking my alpha level and dividing it by 2. Okay? And then I look up in the tail, okay, for what area is associated with 0.025, and then I find the z-score that is associated with that. So this corresponds with the section of your textbook that's called the significance level. I encourage you to work with some of the problems that are listed in that section so that it can give you some concrete practice with this material.